Okay, we're going to start with graphing motion. The first type of graph we're going to look at are technically called a speed graph. Speed is the relationship between distance versus time. How much distance is covered in a given amount of time. We're going to watch a man take several walks to and from this building, and then we're going to see what the graph of that motion would look like. Okay? So he's walking from the building. Okay. So what we noticed, he walked 25 feet and it took him 5 seconds. Okay. So we have a distance parameter and we have a time parameter. Now you're going to see the graph as it forms. Okay, so we have distance. We start at 0, we go to 25 feet. Time starts at 0, goes to 5 seconds. You always need to look at your y-axis when you're looking at motion graphs. If this variable changes, it can mean a totally different thing. Distance time graphs are totally different than velocity time, which we're going to get to in a minute. So as we're looking at our distance time graph, the man walked at a constant rate, which gives us this nice straight line. We call this a linear graph. When you see a graph that produces this straight line, that means that the rate that the object was moving was constant. At any point, we could take the ordered pair and we should be able to use those numbers, solve for speed, and get the same answer at any point on this line. Okay? So what you would do is you would take your distance and divide by your time. So if we came to 5, we came over to the line. We dropped down to 1. 5 divided by 1 should give us a speed of 5. If I come to 10, come to the line, drop down to 2. 10 divided by 2 still gives us a speed of 5. That's what I mean by constant rate. Anywhere along this graph, we have a constant rate. You need to draw this graph now and label that this is distance time graph at a constant rate. Okay, so let's watch this next graph. Our distance is still going to be 25 feet. We're going to keep continuing to graph based off of that distance parameter. And then you'll watch your time down here, and you'll change that axis based on the time that passes. Okay, so what you're going to notice is the man is now walking from away from the building towards the building. Okay, as he's walking away from the building towards the building, I want you to predict, what do you think that motion would be like? Is he starting from point 0 if he's away from the building and walking towards the building? If it's distance from work on our y-axis, okay? Watch as the graph is formed. Notice, because he started 25 feet away from work, okay, we still have constant motion, which means we still have a straight line. Straight line on a distance time graph means constant motion. Same speed everywhere along this line, but he started at a point 25 feet away from work and he moved towards work. So the slope of our line goes down because this is a distance time graph, and he was 25 feet away from the 0 point, or which is considered work. Draw this graph, label it on your paper. All right, in this graph, the man is going to move from away from the building towards the building again. But I want you to notice his rate. Rate is the amount of time it takes for him to do that, okay? He's still covering 25 feet. So pay attention. Notice that he is running, okay? As he runs back towards the building, he's moving at a faster rate. Compare this graph to your previous graph and look at the difference in the slope of the line. When we have an increased rate, a distance time graph will show a steeper slope, okay? When it was a nice slow walk, your line went from 25 over to 5. This time he covered the same distance in less time. So the line is much steeper. Steeper line indicates an increased rate. Draw and label this graph. So this is a constant speed moving towards the building at a faster rate. We have a constant speed towards the building at a faster rate. For the next graph, we're going to look at what it looks like on a distance time graph when motion stops. Right here at this point, the man is standing still. That means that distance is not changing. Okay, so as he walks out of the building, 0.00 down here, and then he pauses here, he does not move. The graph has a flat line. There's no slope. Okay, no slope of the line on a distance time graph. If you come over here to the side, it shows that at 16 feet away from the origin, he stayed in the same position, starting at 3.5 seconds, all the way through 8 seconds. So from second 3.5 to second 8, the man stayed still. On a distance time graph, when you have a flat section of the graph, it means that there is no motion. No motion. So he was constant speed away from the building, then there was no motion, and he continued constant speed away from the building. Okay, so this graph has 3 segments: constant away, no motion, constant away. On this graph, we're going to look at motion away from and then back towards the building. The man moves out, he turns around, and he goes back. So as he moves out, you would have that constant speed away, and then as he moves back, you should see that constant speed back. In the middle, there was the one moment where he paused. Since he paused there for a second, you have a flat section that indicates no motion. So he started at point 0, the building. He walked out 5 feet. At 2 seconds, he stopped for a second. At 3 seconds, he turned and resumed his walk back into the building. This graph is constant away, no motion, constant back. Please draw and label this graph. Okay, so this graph is unique because if you notice, the man is not starting inside of the building, he's not starting away from the building. So at some point in this 25-foot stretch, he is starting not at point 0, not at point 25. Okay, if we push play, we'll see that he stands there for multiple seconds. So about 6.5 seconds pass, he stayed in one spot. Okay, so let's see what the graph would look like of him standing and then moving, but not starting at point 0. Okay, I'm going to pause for a second and let you see. So because he is 5 feet from the origin, we start the graph off right here a little above 5 feet. Notice the line is flat. On a distance time graph, a flat line still means no motion. The man was standing still. Then as he starts to move, he moves at a constant rate away from the building. Now let's look at what a graph would look like if he was not moving at a constant rate. Okay, so we're going to watch the man move from away from the building towards the building. Okay, and you'll notice that he starts out fast and he slows down over time. Then he comes to a stop. All of this occurs over a little bit over 7 seconds. Now watch the graph as it forms. Notice the curve to the line. Okay, we have, rather than having a constant rate, when you have an increase or a decrease in speed, we call that change acceleration. It can be positive or negative. Okay, in this case, he started out fast and he slowed down. Okay, that's when you get this curving of the line. This portion still means that he stopped and then he started to walk again back into the building. He stopped as he opened the door and then he walked back into the building. But this section where his speed was variable, where his distance and time were changing, it was not constant, we call that an acceleration graph. When you have a distance time graph that shows a curved line, that is acceleration. In this case, deceleration. But acceleration, positive and negative, are both called acceleration. Draw this graph and label it as either negative acceleration or deceleration. Okay, now we're going to look at positive acceleration. Okay, positive acceleration. It has nothing to do with where he's located. It has to do with the curve of the line. This time he's leaving work and he's moving away from work. So the graph will start at point 0, down in the corner. But notice, he's going very slow and then he speeds up. So because he started at the building, I'm going to pause for a second. That's why we're starting at 0. The last line, when he started away from work, and the line went down, the line going down doesn't mean negative acceleration. The line going down indicated where he started and where he ended. Okay? What we're looking for when we see acceleration is we're looking for a curved line. Okay? So here he comes. He's walking slowly. And then he speeds up. Okay? That's what creates that curve of the line. A lot of times when you're looking at a graph like this, they may ask you, what portion of the graph, the first 5 seconds or the last 5 seconds, was the object moving faster? You want to look at the steepness of the line. Notice that here at the beginning, the graph is not as steep as here at the end. Because this side is steeper, we can see that he sped up here. The more shallow the line, the slower the motion. The steeper the line, the faster the motion. draw this as a positive acceleration graph now. Okay, we have positive acceleration, meaning that he sped up. Okay, in this example, we're going to see a lot of the different components all put together in one example. First, watch the man's motion. He comes out, slows down, and then returns back to the building slowly and speeds up. Okay, so I'm going to repeat that. He came out quickly, slowed down, then returned back to the building. And when he returned back to the building, he started slowly and he sped back up. So in this example, we see him moving away from the origin, back towards the origin. So he's starting at 0, he's moving away, and he's moving back. So we're going to have some kind of line that goes up and some kind of line that goes back down. But it's not constant motion because he starts out quickly and slows down. We have deceleration or negative acceleration, and then he starts slowly and speeds back up as he moves back into the building. We see positive acceleration. Okay, so let's look at what that looks like. So as he slowed down or decelerated, we see our line curve. Then he's going to stand here for a second. We now know that when there's no motion, distance remains the same. Then he slowly turns back towards the building, and then he speeds up as he moves back into the building. So what we get is a graph that shows moving away and slowing down, deceleration, standing still, moving back, and speeding up. Draw this graph and label it now. Okay, so you can also calculate speed from a graph. We're going to look at how you do that, okay? I have a distance time graph. Before we work on calculating speed, there's two things to consider. The first thing is, do we want instantaneous speed or average speed? What that means is instantaneous speed is speed at any point along this line, okay? So if we picked any one point, found the coordinate pair, and found the speed at that moment, at 25 seconds, at 15 seconds, at 5 seconds. Average speed is the total speed found over the entire trip. In order to solve for average speed, you have to pull your final distance traveled and use your final time taken, okay? So there's two types of speeds that you can calculate for. Little side note, on a distance time graph, if you were asked to find the speed along a flat portion of the line, you should automatically know that speed would be 0. If distance is not changing, then speed would be 0. So don't waste your time trying to calculate there, because a flat portion on a distance time graph indicates no motion. Speed would be 0. Okay, so let's look at our two examples. We're going to look at average speed first. Okay, and we take an inventory of what we're given. So I come up here. What is my distance at the end of the trip? Okay, my distance is 4 kilometers. So I write that 4 km. Always look at your units on your y-axis. The amount of time taken was time in minutes. It took 40 minutes. Okay, so I have my distance and my time. I can solve for speed. Distance goes on top, time goes on bottom, and I am solving for speed. I know that I have a smaller number on top. That does not matter. You always divide top number by bottom number. Okay, our final answer is 0.1 km per minute. I do not have to put a direction because it only asked for speed and I did not know a direction, okay? I don't know if this person went north or south, okay? So let's look at an instantaneous speed calculation. The question asks for the instantaneous speed at 25 seconds. This is where you're going to pull your coordinate pair using your graph. 25 seconds, and I'm going to come up to the line, okay? And then I'm going to come over here and draw as straight a line as I possibly can. And we're almost to 3. 25 seconds is just a little bit below 3. I'm going to leave it at 3 for simplicity's sake, okay? We could say 2.8, but I'm just going to use 3 as my distance parameter, okay? So 3 goes on top, and it's still kilometers, and 25 minutes goes on bottom, okay? And I'm solving for speed, okay? So my inventory was a 3-kilometer distance and a 25-minute time. Again, top number versus bottom number. Always divide the top by the bottom. That gives us 0.12. 0.12 what? What units do I put? When I have a speed, I need a distance parameter and a time parameter. So I put km per minute. And this is how you can use the coordinate pair from a graph to solve for speed.